Welcome to EPG Pathshala. Today we are going to discuss on pyrolysis, a thermochemical conversion process. Pyrolysis technology is similar to that of combustion and gasification as per the thermochemical conversion for the energy production, but it differs from this based on the absence of oxygen for the thermochemical process. Pyrolysis is gaining importance in the recent decades for the production of bio-oil from the biomass. Pyrolysis, the main product of pyrolysis is pyrolytic oil or bio-oil. The goal of this process is to optimize or maximize the value addition to the biofuel. It has a high heating value also. This pyrolysis helps in the cogeneration process of bagasse, as well as nowadays the municipal solid waste is also used for the pyrolysis process for energy production. Pyrolysis can further be used, or the product of the pyrolysis can be used for biodiesel production and highly value added other chemicals and the fuel. In this module, we will be discussing on pyrolysis process, how pyrolysis differ from combustion and gasification, what are the properties of bio-oil, which is the main product of pyrolysis, how the bio-oil quality is varying, what are the different types of pyrolysis. We will also see what are the different types of pyrolytic reactor or pyrolyzers, what are the factors affecting pyrolysis, merits and demerits of bio-oil production. The word pyrolysis derived from two Greek words, pyro, which means fire, and lysis means separation. It is a process of thermal separation of different components of a conjugate material. There is changes of both physical state and chemical composition of substance happens during this process. So, the pyrolysis is the process or thermochemical conversion process of an organic material, mostly producing liquid, solid and gas. This process is also known as carbonization, where the organic matter are thermally converted to carbon, also known as destructive distillation. So, the pyrolysis differ from combustion and gasification. Upon heating, biomass loses mass in the form of moisture, volatile matter and carbonaceous materials in the process of combustion and gasification. Further, while heated in air environment, at some point it attains ignition temperature and start burning, liberating heat, moisture and carbon dioxide. If the biomass is heated in absence of air or in the presence of inert atmosphere, that is nitrogen, helium, argon, etc., decomposition is only thermal and the process is known as pyrolysis. So, pyrolysis happens in the absence of air, while combustion and gasification occur in the presence of air. In combustion, excess of air is used, in gasification, limited supply of air is used. The pyrolysis is known as destructive distillation and it produces volatiles, condensates like tar, biochar, which is normally charcoal, depending upon process variables and the temperature, reaction temperature. What is the basic difference between the pyrolysis and gasification? Gasification occurs under controlled flow of air or oxygen, and the process involves partial oxidation of carbon present in the biomass, and gaseous mixture is most desirable product, which is commonly known as syngas or producer gas. Instead, in pyrolysis, oxidation should be prevented as much as possible to get a desired end product of good quality liquid fuel, that is bio-oil, and solid mass in the form of charcoal or biochar along with some gaseous compounds. The direct combustion of biomass for heating in steam boiler or furnace is considered as inefficient biomass conversion process compared to gasification and pyrolysis. And also the direct combustion process generates more pollutants in the form of carbon monoxide, oxides of nitrogen and particulate matter in the form of fly ash. So, high value fuel products are produced by the pyrolysis process. The compatibility of the process is that it can be adjusted according to the product we need, such as charcoal, pyrolytic oil or gas based on our requirement. So, this schematic diagram shows the pyrolysis of biomass. So, biomass undergoes the pyrolysis while heating with no air condition, and it produces bio oil, which is the liquid product after condensation, and the combustion produce the condensation of this, it also produces the gaseous, and the rest over the remains the solid residue is known as char or biochar. During the course of pyrolysis, volatile and extractives such as lipids are recovered faster, followed by cellulose and hemicellulose, which form mainly volatile products due to thermal cleavage of the sugar units. Lignin forms mainly char, since it is not readily cleaved to lower molecular weight fragments. Production of char due to cleavage of lignin also depends on content of methoxy group present in the lignin component of the biomass. Lignins with low methoxy group from softwood species produce higher char than hardwood lignins. This is the flow diagram of a pyrolysis reactor or pyrolysis in which the pyrolysis normally happens. So, the biomass undergo drying, which is subjected to grinding, and then it is added to the pyrolysis reactor, where the char removal occurs and the bio oil which is quenched and the gas is removed, while the gas can recycle if it is needed. So, this is the pyrolysis reactor or pyrolysis process occur in the reactor. So, the product of pyrolysis, the major product of the pyrolysis is bio oil. It is around 75% with the liquid one, liquid fuel, and the solid and gaseous accounts 12 or 13%. Pyrolysis liquid, which is referred as pyrolytic oil, bio crude oil, biofuel oil, wood liquid, wood oil, liquid smoke, wood distillates, pyrolignous tar or pyrolignous acids. These are the synonyms or the terms which are used for the pyrolysis liquid fuel. This liquid product consists of two phases, an aqueous phase which comprising a wide variety of organo-oxygen compounds of low molecular weight, and non-aqueous phase containing insoluble organics, that is mainly aromatics of high molecular weight, which is known as the bio oil or tar. The ratios of acetic acid, methanol and acetone of aqueous phase were higher than those of the non-aqueous phase. The pyrolytic oil fraction so mainly contains organic acid, aldehydes, ketones, phenols and anhydrous sugars with significant quantities of water. So, it is a complex of highly oxygenated hydrocarbons such as esters, ether, aldehyde, ketones, phenols, carboxylic acid and alcohol. Bio oil has a content of water in the range of 15 to 30%. It is derived from moisture in the feedstock and the dehydration process during the pyrolysis reaction and storage. The presence of water has both negative and positive effects on the oil properties. It lowers its heating value, contributes to increase in ignition delay and decrease in combustion rate compared with the other engine fuels. But it also improves bio-oil flow characteristics, reduces the oil viscosity, which is beneficial to the combustion process. Bio-oil usually have oxygen content within 35 to 40% distributed among compounds depending on the resource of biomass and factors like temperature, residence time and heating rate of the pyrolytic process. High oxygen content leads to lower energy density and immiscibility with hydrocarbon fuel also increased. The strong acidity of bio oil makes them extremely unstable and reactive in nature. It shows wide range of boiling temperature due to complex composition, and during the distillation the slow heating rate results polymerization of reactive components. So, it starts boiling below 100 degrees Celsius, stopping at 250 to 280 degrees, it leaves 35 to 50% weight as solid residues below and above the 250 to 280 degrees Celsius. The solid residues occurs instead of oil production. The high heating value of bio oil is in the range between 15 to 19 megajoule per kilogram. The properties of bio oil depend on factors such as biomass feedstocks, production process, reaction condition and collecting efficiency. Usually, the bio oils have lower heating value in comparison to the fossil fuel. Let us see what are the feedstocks used for the pyrolysis. Mainly bagasse, the byproduct of the sugar industry, which is the solid residue left over after the juice extraction, is used for the pyrolytic action or pyrolytic process for energy harnessing. Another one is woody and herbaceous species like woody biomass, pine wood sawdust, salix wood chip, other forest woods can also be used for the pyrolysis. Agricultural and industrial waste like rice straw, rice husk, bamboo straw can also be used for the feedstock. Aquatic and algal waste can also be used for this process. Nowadays, municipal solid waste is used for the pyrolysis or for the energy recovery. So, depending upon the types of biomass feedstock and their composition, the pyrolysis behavior also vary from each other. Let us see what are the types of pyrolysis. There are 3 types: slow, intermediate and fast pyrolysis, depending upon the operating temperature. If the temperature is low, that is around 450 degrees Celsius, the retention time is higher than 1 hour, the process is called slow pyrolysis. Very slow pyrolysis has been traditionally used by the communities to produce charcoal from woody biomass. When the operating temperature is very high, that is 550 to 800 degrees Celsius, and the retention time of the gas phase is extremely low, that is less than 2 seconds, the product yield is mostly liquid, that is bio oil, and the process is known as fast pyrolysis. High tar products predominate in this fast pyrolysis due to high temperature, which facilitates increased fragmentations, isomerization and polymerization. In intermediate pyrolysis, the liquid product is of superior quality as compared to fast pyrolysis, and here the operating temperature is relatively lower, that is in between 450 to 550 degrees Celsius. So, based on the operating temperature, the slow pyrolysis occur when the temperature is less than 450 degrees Celsius and the retention time is high, and the product mainly will be the solid content or the charcoal. In the case of fast pyrolysis, it is at higher temperature, it occurs at a higher temperature and retention time is very less, and the product will be the oil, bio oil. And intermediate pyrolysis occur in a temperature between 450 to 550 degree Celsius. Among these, the fast pyrolysis is the most efficient one, and the most of the research is going on to have a best method of fast pyrolysis. The essential features of fast pyrolysis reactor are: it should have very high heating and heat transfer rates, moderate and carefully controlled temperature, and rapid cooling and quenching of the pyrolysis vapors. Let us see what are the types of pyrolysis reactor. The 5 major types of reactors through which the fast pyrolysis occur are ablative pyrolysis, bubbling fluidized bed pyrolysis, circulating fluidized bed and transported bed pyrolysis, rotating cone pyrolysis, vacuum pyrolysis reactor. Ablative pyrolysis. In this process, biomass particles are moved across a hot metal surface, resulting the outer layer of biomass to pyrolyze, and a thin film, that is around 10 microns of liquid material is deposited on the metal surface. Heat transferred convectively from the metal, rapidly vaporizing the liquid film, that is 95% conduction, 4% convection and 1% radiation occurs. Although the surface of metal is hot, that is around 550 degrees Celsius, the area surrounding the surface can be much cooler. By contracting solid biomass particles with a hot surface, the material can be rapidly pyrolyzed and resultant vapors can be quickly removed from hot reaction zone to quench further reactions. The biomass particle remains at a low temperature and reacts only when it physically contacted the hot surface. Continuous vaporization of the thin layer of biomass as it passes over the surface reduces the particle size in an ablative manner, and only little amount of char is formed. The reaction rate are not limited by heat transfer through the biomass particle, which facilitates the use of large biomass particle. Here it is limited by the rate of heat supply to the reactor rather than the rate of heat absorption by the pyrolysing biomass. There is no requirement of inert gas, so processing equipment is relatively smaller and reaction system is thus more intensive. And also the absence of fluidizing gas substantially increases partial pressure of condensable vapors, leading to more efficient collection and smaller equipment. This process is surface area controlled and upscaling is costlier, and the reactor is mechanically driven that enhances its complexity. The next type of pyrolytic reactor is bubbling fluidized bed. In this technique, the transfer of heat takes place from a heat source to the biomass through dual modes of convection and conduction process, 90% conduction, 9% convection and 1% radiation. To achieve high biomass heating rates, biomass particle size of less than 2 to 3 millimeter are needed in this process. It is also important that rate of particle heating is usually the rate limiting step. Residence time of solids and vapor is controlled by fluidizing gas flow rate and is higher for char than for the vapor. As char acts as an effective vapor cracking catalyst at fast pyrolysis reaction temperature, rapid and effective char separation and removal is important, and it is usually achieved by ejection and entrainment followed by separation in one or more cyclones. The high level of inert gases arising from the permanent gas flows are required for fluidization, which results in very low partial pressure for the condensable vapor and thus requires appropriate design and efficient operation of heat exchanger and liquid collection system in this type of reactor. The third type is the circulating fluidized bed and transported bed pyrolyzer. These systems have similar features that of bubbling fluidized bed, except that the residence time of char is almost the same as for vapors and gas, and heat transfer takes place through conduction, convection and radiation. Here 80% conduction, 19% convection and 1% radiation. And also the char outflow is favored due to higher gas velocity, leading to higher char condense in the collected bio oil, unless more extensive char removal is included. This char is recovered with the sand and burnt in a close coupled combustor to reheat the sand, which is then recirculated. In this type, heat supply is usually from recirculation of heated sand from a secondary char combustor, which can be either a bubbling or circulating fluid bed. Thus, the process is similar to a twin fluid bed gasifier, except that the reactor temperature is much lower and closely integrated char combustion occurs in a secondary reactor. The next type is the rotating cone. The basic principle of this process is that rapid heat transfer from solid surface of a rotating cone to small wood particles. These are mixed for better heat transfer with sand or with a catalytically active material. In a rotating cone pyrolysis reactor, the biomass particles are introduced at room temperature along with hot sand near the bottom of a cone. They are mixed and transported upwards by the rotation of the cone. The pressure of outgoing materials are slightly above the atmospheric levels. Rapid heating and short gas phase residence time can be easily achieved in this reactor. This diagram shows the fluidized bed and rotating cone type reactors. And the fifth type is vacuum pyrolysis reactor. In this technique, biomass materials are heated in vacuum in order to decrease boiling point and avoid adverse chemical reactions. The basic technology, it was developed by the University of Laval using a multiple hearth furnace, later converted to purpose designed horizontal moving bed. In vacuum pyrolysis, residence time of the substrate at the working temperature is limited as much as possible in order to minimize secondary reaction. This system is not a fast pyrolysis as heat transfer rate to and through the solid biomass is much slower than in the other types of reactors. What are the parameters affecting the pyrolysis? The parameters include type of biomass which are to be used for the pyrolysis, dryness, it prefers less than 10% moisture content in it, the size of biomass particle, type of the reactors, retention time and temperature. Physicochemical characteristics of bio oil like water content, oxygen content, viscosity, acidity, heating value and ash content are important parameters which determines the quality of bio oil. What are the benefits of the pyrolysis product? Bio oil has great potential value as fuel and chemicals. Since this contains very less amount of nitrogen content, it can be used as heating oil in furnace. It can be potentially upgraded or refined to produce liquid transportation fuel and organic chemical. Thus, it has a high value addition to it. It produces bio oil and biochar, both have fuel value or the calorific value. It is considered as a clean fuel because it produces less amount of the toxic compounds and the oxide emission is also very less, or you can say it is negligible because oxygen is not used in the combustion process. But bio oil is acidic within a pH range of 2 to 4, and because of that it is highly unstable and corrosive in nature, and it is difficult in the transportation and storage. Here it should be stored in stainless steel containers because of this acidic nature of the bio oil. The freshly made bio oil can be pumped and transported through pipelines, and later on its viscosity increases, that is viscosity increases with the time. So, it is also a problem in using it as a fuel. So, because of the fact that bio oil can undergo oxidative and thermal degradation resulting in large molecular weight polymer compounds, hence unprocessed bio oil cannot be readily mixed with petroleum derived fuels, particularly for any other engine. So, an upgradation of pyrolysis oil is required. The bio oil contains high proportion of oxygenated compounds, viscous, acidic in nature. The compounds are viscous, acidic and acidic in nature. So, it is thermally unstable and can undergo secondary reaction to yield high molecular weight polymers. We have seen the limitations. So, in order to upgrade the properties of the bio oil, there are different processes to produce the high grade fuel and chemicals. Some are hydrotreating, catalytic cracking, emulsification and steam reforming. So, students, in this module we have discussed about pyrolysis process, how it differ from combustion and gasification, and what are the advantages of pyrolytic process over the combustion and gasification process. And the main product of pyrolysis we have seen is bio oil along with biochar, and we have seen different types of pyrolysis like fast pyrolysis, intermediate pyrolysis and slow pyrolysis based on the operating temperature. You have seen that if the temperature is below 450 degrees Celsius, it is a slow process which results in the production of charcoal. If it is between 450 550, it produces the liquid fuel, and the fast pyrolysis means the most efficient one where the temperature is above 550 and the residence time is less, producing the bio oil, and the quality of bio oil depends upon the feedstocks used for the pyrolysis process. We have seen that different feedstocks like woody biomass, agricultural and industrial waste and MSW, that is municipal solid waste, and some algal waste can also be used for the pyrolysis process. And we have seen different types of pyrolytic reactors. The major ones are ablative type, fluidized bed, vacuum rotating corn, etc. We have seen they differ, how they differ in the process like conduction, convection, radiation, and the products produced by the means of these different type of reactors. We have seen different factors affecting the pyrolysis process like water content, the type of the reactor, residence time, temperature, etc. We have seen that bio oil or the merits of pyrolysis products, it is a clean process which produces high value this energy. It has what to say, the bio oil has different advantages like it can be used or further can be refined to make another fuel as well as some other chemicals. And we have seen this bio oil has some limitations like its viscosity, its acidity. So, it requires upgrading or upgradation for the further use in the engines. Thank you.